Welcome everyone to this fourth webinar hosted by the SWAN APAC Alliance. The Alliance is a part of the SWAN, or Smart Water Networks Forum, a non-for-profit which is the leading global hub for the smart water and wastewater sectors.
Our speakers today will include an introduction by Dr. Shanshan Chou, General Secretary of the Water Affairs Organization, followed by 4 presentations from Thomas Debruyne of our APAC Digital Manager at Veolia, Dr. Paul Y. Chou, Deputy General Manager at Stantec. There's a slight caveat to his presentation. He'll be presenting on smart water supply journey. We also have Dr. Bo-Chuan Chou, CTO of GSD Technologies, and Paul Hart, the Regional Director of Australasia for Metasphere. We want to make this session as interactive as possible, so please direct any questions to the speakers through the Q&A box during the presentation itself.
So here is a snapshot of SWAN's global members, which represent the full spectrum of stakeholders in the industry from idea to pipe. So the SWAN APAC Alliance works to accelerate smart water and wastewater development in the Asia-Pacific region through the SWAN Forum's collective industry expertise and collaborative partnerships. So the Alliance offers access to specialised webinars, workshops, and is a central source for smart water and wastewater information. You can learn more on the Alliance homepage.
So the SWAN APAC Alliance is led by George Theo, the CEO of Unity Water, and is supported by the 3 subgroups that focus on regional partnerships, research, and communications. Alana and myself will moderate the communication, we're the leaders of the communication subgroup. We're also going to moderate today's presentation. I also wanted to take this opportunity to give special thanks to the Alliance's Abstract Review Committee, and it's a team that currently includes Peter Prevost of Colibin Water, Rita Narangala of Yarra Valley Water, and Rob Main of Hunter Water. Thanks so much for bringing your ideas and providing integrity to the abstract review process that made this presentation possible today. So here's a list as part of the APAC Alliance of the innovative Alliance partners, which include 18 utilities collaborating to advance smart water in the region. If you're not yet a lead partner, we invite you to come join us as part of this.
For the last couple of years, its first workshop took place last year in Noosa Heads in sunny Queensland, 3 webinars on innovative industry breaking topics, a smart water forum at the last Singapore International Water Week, and a session at the MYWAC conference in Malaysia. So although 2020 has been a really interesting year for all of us in regards to events, we have some creative platforms for knowledge sharing lined up for 2021, which we'll share with you when we have some further details for you all.
SWAN's value is demonstrated through global and regional collaboration. So this diagram you see here is an example of the digital twin work group where leading industry professionals work together to create the digital twin architecture. And this helps utilities successfully simplify and navigate on their smart water journey. When you join the Alliance and are a member of SWAN itself, you receive full access to the research reports, the white papers, webinars, conference recordings, and digital roadmaps to guide you on your smart water journey as a utility or a council, no matter what your maturity is on your journey. So before we start, I just wanted to give a reminder, if you have questions along the way, please add them to the comment box, and we'll have time at the end of the presentation to ask the presenters themselves for further follow-up questions. I would like to now hand it off to Thomas for his presentation.
Actually, we'll be going to Dr. Chou, who has joined us.
She has? Okay,
yep.
Great.
Wonderful. Take it away, Dr.
Thanks,
Chou.
Lana.
So hi everybody, I'm Shanshan from National Jiao Tong University. I'm also the Secretary General of Water Affairs Organization, Taiwan. So it's my pleasure to present development status of smart water and wastewater platform in WAOT. So next, let's introduce WAOT first. It's a close co-work partner with industry, government, university, and institute to develop water industry, including low water, drinking water, wastewater, and new water. And we also the exchange platform for business and technology. Especially, we focus on smart water and wastewater technology. So we recommend 2 members of WAOT. One is from GSD for smart wastewater, and the other one from Stantec for smart water. Later, they will have 2 presentations. So next. Actually, we just held the Intelligent Water Forum 6 days ago in Taiwan. So you can see everyone wear mask in a meeting room. I think it's a special experience since in Taiwan, we still can hold a face-to-face seminar in a COVID-19 year. And we have totally 6 presentations, 2 for water and wastewater from ITRI and GSD. ITRI, Industrial Technology Research Institute, is a very famous institute in the world. And actually, I also work in ITRI for over 20 years. And other presentation for wastewater from ITRI and NCTU, and the other one for smart water from Taipei Water Department and Taiwan Water Corporation. So next. I think in Taiwan, we have good multidiscipline integration opportunity. Since Taiwan has many good AIoT and ICT component company. So from the digitalization, visualization for IoT, and then to data analysis, data algorithm for AI. Taiwan has good AIoT hardware and software capability. And ITRI and WAOT members help Taiwan government to build up some demo sites. So from the intelligent component to intelligent process, then intelligent total solution. So we have many demo sites for different applications. So next. So this presentation show the prescriptive analytics developed by NCTU, that is optimal model. So AI can determine the lowest cost according to the removal of COD, color, or turbidity from the model. So you can see about 20 to 40% of operating costs can be reduced according to the AI decision. Next. So this slide, I just show the smart water status in Taiwan. And 2 famous case study. One is smart water network in Taipei City, including the low water treatment plant, and then to end user. From low water monitoring and clean water quality control. And another one is the smart water meter. So the benefit is about 40% of water leakage can be reduced, and 30% of power consumption can be reduced. And another successful example is a smarter water supply in Matsu Islands. So later, Dr. Chou will show for you. So next. Finally, I just show the smart wastewater status in Taiwan. So you can see the smart wastewater management platform developed by ITRI and GSD. The right side is the remote control centers developed by ITRI. And the left side, you can see 5 layers developed by GSD, except 3 common IoT layers in the middle. GSD added 2 layers. One is in the bottom, the equipment layer, and the other one is the top layer, decision maker layer. Okay, so thanks for your attention. So now let's welcome the next speaker, Thomas, please.
Good morning, everyone. Can you hear me well?
Yes, we can hear you.
Yes, thank you. All right, can you see my screen well? Good, it looks like I'm sharing. So good morning to you all. First of all, I would like to thank the Smart Water Alliance Network for allowing me to present this exciting project today. We'll get going quite fast because we have a lot to cover in 10 minutes, but feel free to ask any question you may have during the Q&A session at the end. So today we are going to cover the system thinking approach to asset optimization. And if you give me a minute, I'm going to hide. Yes, that's better. To asset optimization. So what does it entail exactly? First of all, we're going to present what integrated plant network approach is about and how it has improved overall performance, but also we are going to go through model predictive control, MPC in a nutshell, and how this has helped the utility and Veolia to improve operational decision. So we're going to talk about a project that took place in Denmark, right in the center, in the middle, at a location called Kolding, utility being BlueKolding. As you can see, we have a combination of combined sewer system as well as separate sewer system being treated at a wastewater treatment plant located in AQUAVISTAT. Okay, so today we're going to focus on combined sewer system and associated control, plus of course the wastewater treatment plant. And have a look at the challenge first. So the combined sewer overflow were too high. I will provide some numbers later on. We had risks in flood in a populated area, and in a nutshell, we had a need for an extra retention basin of 6,000 cube to be able to cope with it. On the wastewater treatment plant, we had a very high OPEX to do pea precipitation for pea removal and associated sludge disposal, but also issues on the compliance side due to sludge escape from the clarifier, especially during storm water event. So the total overflow at this stage was 150,000 cubes a year of overflow and between 30 to 35 events. And the idea was to reduce to below 6,000 cubes a year and number of combined sewer overflow events of less of 10 events per year. So in 2011, BlueKolding, in collaboration with Veolia Water Technology Kruger, implemented a module called Sewerflex in 2011. And after 7 years of successful operation, we upgraded to predictive control. And that is what I'm going to introduce today. So I'm going to present at a very high level what we did on the sewer side, and then on the wastewater treatment side. The idea is not to go through in detail. We possibly can explain further during the Q&A session, but to present how the integrated approach between both approaches provided benefits between the sewer and the wastewater treatment side. On the sewer side, so let's start first with reactive control versus predictive control. So reactive control, we have a look at the current status on the different storage basin and flow. And the idea is to look at the different control and activate actuators based on level, flow rate, and so forth. The idea was to upgrade to predictive control, considering both the weather forecast, either using the radar data and as well rain gauges, but also the current status of the different storage volume and so forth. And the idea is to, instead of going to say, if the water level, for instance, is at X, then we action at Y, the idea is to predict if the future of the water level estimating a runoff will be X, then we action at Y, being either a gate or a pumping station, for instance. Now, that is updated with measurement and associated set point with a very high granulometry every 5 minutes or so. It's done via a platform called AQUAVISTAT, which is a cloud-based platform from Veolia Water Technology. It is a very highly secured digital portal used by a third and the client. The communication is done via an OPC bridge. And the idea is to calculate the different optimal set points that is going to be calculated using an genetic algorithm that I'm going to present on the next slide, and to communicate back the different optimized set points to the PLC SCADA system every 5 minutes. So it is based on dynamic overflow risk assessment principle that we have developed in-house, considering a few different factors. The water volume, obviously, at the different basins, the expected runoff to come based on the forecast data, estimated uncertainty as well, and risk mitigation. Number 4 is the most important point, the relative cost of the overflow at the different location. And of course, the current state of the hydraulic capacity of the downstream wastewater treatment plant. And I will come back on that later. So if we go through the different steps, it's quite simple, actually. We estimate the different water storage volume at the stage 1, then based on what's to come, the different runoff modeling and the radar forecast, there will be a calculation of the combined sewer overflow risks based on the runoff and specific factors as well of the different basins. After that, there will be some calculation made to minimize the overflow risks based on location across the different catchment. And then optimal set point will be sent to the local PLC SCADA to be action, again, done every 5 minutes. I would like to come back on point 4, which is the innovation behind this. We allocate a cost, which is more or less a risk rating based on the location of the different basins. So the idea is to minimize the event of having a risk, a combined sewer overflow, for instance, where people are going for a swim or close to a high populated area. And if indeed we must have a combined sewer overflow to occur, the idea is for it to occur at a location where there will be the less impact for the community. But also, if we have an overflow starting, the idea is to let the overflow run and to minimize and to actualize the other gates and so forth, so that the overflow continue to take place at the one location, because as you understand, the regulation is based on the number of events and not always based on the number of flows. On the wastewater treatment side, again, very much in a nutshell, we have put in place a mode that we call Stormwater mode. So in a nutshell, it's an operational mode triggered by the inlet flow or the predicted flow and the current activated sludge distribution status in the system. The idea is to retain a higher amount of sludge in the process tank to minimize the sludge blanket level in the clarifier, to minimize sludge escape in case and during a high wet weather event. Now, the settling capacity is based on the activated sludge plant, and I will show you an example just after that. So you might have heard of the system before called aeration tank settling. You have a quick example here on the right where it's simple plug flow activated sludge system. The idea is when the storm water mode is triggered to allow for further settling of the sludge in the aeration basin, in the aeration anoxic remaining section, and a lower MLLS content to go through the clarifier downstream to avoid sludge escape during a high wet weather flow. Now, it is a dynamic system, as we will see after that. It is activated and deactivated based on the weather forecast and the current status of the inlet flow as well. Like for the sewer system, production is everything, and it's changing the way we look at this feature as well. So the forecast data from the radar can provide much greater visibility on the stormwater feature. So for example, here you can see on the chart the current capacity of the plant without stormwater mode and with stormwater mode, because again, it is a dynamic mode. Of course, the idea is not to have a high MLLS in the aeration tank to equalize everything, but to go into stormwater mode only when required. In red, you will have the flow going through the wastewater treatment plant. And if it is triggered by this threshold limit, for instance, and we have a lack of visibility, which we can call reactive actionable, for instance, there will be a limited amount of time during which there will be some sludge escape until the wastewater treatment plant gets ready through the different levers we have at the plant to move the sludge around. If we're able to predict a high wet weather event based on the level we have on the upstream sewer network, but also radar data, we will be able to get the wastewater treatment plant ready upstream and get the plant ready before there is a high inlet flow coming and avoid altogether sludge escape from the clarifier downstream. Now, the idea is to look at the integrated approach and how that integrated control has added one level up of dynamic capacity, considering both the sewer network and the wastewater treatment plant. Now, Sewerflex, which was a module that we discussed about, obviously can predict the inflow into the wastewater treatment plant based on simple modeling and forecast data, which will be, of course, a great bonus to know what's coming to us. But also we can equalize the flow rate during dry weather, as people who understand biological treatment, having a stable flow rate and with hydraulic and biological intake is of great benefits. But also during high wet weather flow, the idea is to optimize the flow using the extra capacity we might have on the sewer side while mitigating combined sewer flow risks as well. So it is always considered, and I will go a bit fast because I'm late, as a combination of conventional upgrade and upgrade using SMART in a nutshell. So the status before, as explained in the introduction, was our current retention basin of 800 meter cube. We could have gone using traditional thinking to 6,000 cubes to be able to overcome the issue we have at the start. And we came down in 2011 in upgrading the retention basin to a much lower capacity, providing savings of 2 million euro. But on the top of that, implementing advanced control and predictive control in place to ensure that we remain compliant and at the same time use both capacity in combination of the sewer and the wastewater treatment plant. To conclude, that's a slide of the current benefits. We've been working with BlueKolding for 20 years now. The benefits you see here on the right have been provided by the features we talked today, but not only. We have implemented other optimization features as well. We won't have time to go through them today. I will be happy to do so at a separate call if you like. and that has been providing great benefits to BlueKolding and Veolia at the same time. Thank you for your attention.
All right. So ladies and gentlemen, my name is Chou from Stantec Consulting Services. I'm very happy to be here today and be able to share with you a little story about Matsu, where smart water is currently being implemented. This is just an overview. I'll be talking about background, issues and challenges, Matsu's approach, the current works, early gains, and also what's ahead of us. Okay, so just to give you an idea where Matsu is located, you can see from the middle picture, that's a zoom-in picture from where Taiwan and China are. Matsu, the red dot in the middle, is fairly close to China, about 10 kilometers away from the Chinese coast, while being much further away from Taiwan, about 200 kilometers. And that remoteness and distance from Taiwan is one of the challenges logistically. Matsu is actually ruled and governed by Taiwan. So Matsu is actually made up by five different islands with just over 12,000 people overall, so it is fairly small. However, the water supply situation there is a little bit complex for the small population. So among the 5 islands, there are 17 natural storage reservoirs, there's 6 water treatment plants, 5 desal plants, and also in the drinking water networks, there are 51 storage tanks. These are treated water. And also each island is independently supplied, which means there's no cross-island supply available. And all of these are being managed by Lianjiang Waterworks, or LCW. That's the responsible local water utility. A lot of the issues and challenges for LCW are actually related to its remote location. So aging infrastructure and supply and distribution, it's faced by almost every other utility in the world. However, the remote location is a disadvantage for LCW because it means world-class solution providers and equipment vendors are less likely to be attracted to such a small island to sell their best products. And also being so remote, you don't see a big influx of fresh graduates or experienced engineers to come and work in such a small place. So there's generally an insufficient skilled or experienced operators for LCW. And also more generically, there's a shortage of manpower in LCW, and that's already affecting their customer services. On the management side, currently there's a lack of means for information to be shared across different islands. And also the level of monitoring is insufficient. So it's a bit hard for LCW to be able to see and hear what's going on some of the other islands, and to explore and find out about problems, and let alone to actually improve on their supply efficiency. So in order to overcome this, Matsu has developed its own smart water roadmap, and it's a 2-phase process. Phase 1, which started in 2018 and is supposed to end this year, is still ongoing, but we're sort of towards the end of phase 1 right now. So phase 1 focused on infrastructure improvement. And if you look on the left-hand side, you'll see 3 boxes: reservoirs, water treatment plants, and networks. This is because LCW, this local utility, is not just responsible for the water networks, but also for everything from raw water to treatment to distribution. So it is a catchment to tap roadmap they're rolling out. So they're trying to improve the infrastructure within phase 1, and after that foundation has been laid, and once all the data information start flowing, they'll be ready to move into phase 2, which will focus on smart analytics to establish baselines, to identify bottlenecks, and also to resolve events at a much faster rate. And eventually, LCW wants to be able to achieve what they call smart services, which on the right-hand side, you'll see include more efficient operations, better water quality, and also better customer experiences overall. So phase one took place between 2018 and still happening to date. And part of it is to make sure this catchment to tap approach, all the way from raw water to finished water, infrastructure can be built up to support the next phase smart water solution implementation, and also to make sure LCW is able to look at all the data information from their head office. Underneath in the table is just a summary of major items and quantities. More notably is the AMR meters. So this is a 100% coverage AMR system. So across the 5 islands, every single account would have an AMR meter installed. I believe that's the first of its kind in Taiwan, and maybe same for Asia. So these are just some of the pictures. There's a control center, server room built for purpose, and then the various installations, flow meters, water quality sensors, etc. There's already been some early gains opportunities, and LCW made sure that these have been captured. So on the left-hand side, with AMR, you don't have to wait for and rely on your meter readers to come back every 2 months before you can identify a usage problem. So this is what happened. They look at the AMR usage, and LCW found out this local restaurant in the picture here to have an unusually large usage. So they decided to pay them a visit. So together with the owner of the restaurant, they quickly found out that they left the tap running in the backyard. And turning this off helped the owner save 92% of their water bill in the next water bill. So although, you know, this is beyond the customer meter, and whatever gets wasted actually gets paid to LCW, but you know, this is about being ethical on an island that has you know, water resources restrictions. So you got to do the right thing, basically. On the right-hand side, also under the AMR system, leaks are quicker to be identified and to be repaired. So what's ahead for Matsu? Over the next 3 years, the focus would be on the smart analytics and using it to make sure benefits can be derived for both the utility and also for the customers. Initial successes of Matsu has also boosted confidence levels for many other utilities across Taiwan. And some of these utilities are already planning similar things for their own water supply. So this would mean business opportunities for all of us. And with that, I conclude my presentation. So over to Dr. Chou.
Okay, thank you, everybody. Good morning, ladies and gentlemen. I am Bo-Chuan, GSD's Chief Technology Officer. It's my honor today to share with you the topic AIoT Process Control Management Platform for Water and Wastewater Treatment System. AIoT Process Control for Water and Wastewater Treatment application is one of the developed strategies in GSD's AIoT Resources Management Platform. The purpose of AIoT Process Management Platform is to optimize operational performance in water and wastewater treatment system. This AIoT Process Control Management Platform includes intelligence process monitoring and control modules, and AI simulation and prediction models, which are developed by the edge data collection and computing from water and wastewater treatment processes. Being consisted of biological and chemical programs, this AIoT process control management platform aims to achieve the objectives of operation, energy, and expenditure optimization through procedures of real-time monitoring, dynamic control, intelligent operation, and AI tuning. There are 8 intelligent process monitoring and control modules, 4 AI control generation models, and 4 AI simulation and prediction models in biological intelligent control and the AI management program, which can be applied to A2O, AO, and activated strategy processes. The operational results show that the total nitrogen, ammonia nitrogen, and the total phosphorus removal rates can be increased to 79.8%, 94.5%, and 99.5%, respectively, by biological intelligent control and the AI management platform. Gross average power saving are 32.3%, 31.9%, and 46.1%, respectively, in A2O, AO, and activated strategy processes. Total power saving are 24.7%, 33.1%, and 59.8%, respectively. The Chemical Intelligent Control and AI Management Program includes 8 intelligent process monitoring and control modules, 1 AI control generation model, and 2 AI simulation and prediction models for chemical neutralization, oxidation reduction, coagulation, and precipitation reactions, and advanced oxidation processes. During the Chemical Intelligent Control and AI Management Program applied to the semiconductor wastewater treatment plant, the saved chemical dosing cost is $2,206 per month, and the sludge disposal expense is $2,082 per month, based on the water quality 5,600 cubic per day. Our verification cases reveal that DSD AIoT intelligent control and the AI management platform have distinguishing features of real-time dynamic control, empirical knowledge in collaboration, control decision mastery, control module independence and adaptability, control target accuracy, and intelligent control optimization. Thank you for your listening.
So good morning, everybody. Thank you very much for your time and for SWAN for the invitation to present today. My presentation is on smart wastewater systems, moving from reactive to proactive. So just a quick introduction to Metasphere. We have 30 years telemetry and remote monitoring experience in the water, wastewater, gas and environmental and transport sectors. And our mission is to use the power of telemetry to drive sustainable use of the world's natural resources. We undertake lots of remote monitoring, different applications from rain gauging through to pressure and flow, river and dam levels and water quality. But sewer monitoring is probably our most common application. And within sewer monitoring, we get involved in sewer level, velocity, flow and H2S monitoring. But sewer level and alarming for sewer blockages and spills is probably our most common application. And there's a few high profile clients on the right hand side there that we undertake this work for. There are a lot of very good reasons to invest in sewer level monitoring and alarming. Preventing sewer blockages and overflows can support utilities and councils in many ways. It certainly helps improve the smooth running of their operations, not having to deal with blockages and spills. It helps to meet regulatory compliance and reporting. It helps to avoid environmental agency fines, which are becoming more prevalent and harsher as time goes on. It helps improve customer and community experience and satisfaction. Fewer spills and disruption means less human waste in parks and communities, and indeed even in people's homes, which in turn helps reduce the health and safety risk to both the community and utility and council crews that have to deal with it. And it also helps to prevent reputational damage. No council or utility likes to be in the news on the front page of any papers for the wrong reasons, particularly sewer spills. There are many challenges associated with sewer level monitoring. It is possibly one of the hardest remote monitoring applications to undertake successfully. Some of the challenges include the simple fact that population is outgrowing the sewer network capacity. Much of the sewer network in major cities is aging, leading to an increase in sewer failure and collapse rates. Community education is an ongoing challenge, trying to prevent the wrong things being flushed down toilets and into sewers, which of course leads to blockages, fatbergs that we see in the news, and general issues. It is, for those working in the sewer environment, a potentially dangerous environment. Build up of gases, confined space, working from height are all very real challenges for this kind of work. Technology, it's a very harsh environment for technologies to operate in. The build-up of gases does cause a lot of issues, high relative humidity. So yeah, it's a very challenging, possibly the most challenging environment for technology to work in. The cost of existing technology and specifically the installation costs at the moment is too high for mass deployment. And mass deployment is required to gain the big data required to undertake or to develop smart wastewater networks through AI or ML. And alarming and response times still remain largely reactive rather than proactive. You may get a few minutes or up to half an hour's warning time of a potential blockage or spill, but that still remains a challenging timescale for utilities or councils to respond within. So more and more, the ambition of utilities and councils that we see is that they are trying to move from being reactive to proactive, and to try and use the power of AI and ML to gain predictive intelligence, and ultimately to try and get ahead of an event, to try and be able to predict when an event is going to happen before it has, and to take action to prevent it from occurring. So the trends we see within the industry are that predictive intelligence via AL and ML requires big data. This requires mass deployment of sensors across the network. And some of the big questions which the utilities and organisations are grappling with are how to mass deploy sensors across a whole network cost effectively, how to handle thousands of incoming data points and alarms, and how to process all that data into something useful and proactive. So Metasphere have recognised that industry trend, and we have developed a new umbrella suite of systems called MetaSense. We believe it's the next generation of remote monitoring to enable cost-effective mass deployment of IoT sensors to gather wide area data required for predictive intelligence to allow the users to get ahead of the event and take action. The first of those solutions under the MetaSense umbrella is what we are calling Hart Sewer, and I'm proud to introduce it today. It was launched to the market just yesterday. It's our new full solution for wastewater network monitoring, combining the four following elements. The top element is, and the most important, is what we're calling Hart, which is our data analytics and insight platform. It's our AI ML platform that combines live and historic rainfall and sewer data to be able to detect and issue alerts for blockages and spills before they occur, which will help utilities and organisations move from being reactive to proactive. Then we have Pallet, which sits below that, which is our tried and tested platform, but has been recently developed to include RESTful APIs so that data can be pushed to anywhere that a client wishes. Then supporting that is our new data collection and processing platform called Canvas, which we specifically developed to be able to map bulk device management for hundreds of thousands of devices. And underpinning it all is a device we are bringing to the market called Sense Level, which is a radar level and IoT telemetry unit all in one. It's NB-IoT, ATEX and IP68. This full solution is being brought to the market at a price point that we believe will facilitate the mass deployment and allow utilities to gather that wide area network across visibility of the whole network, to be able to gather that big data, to be able to seize the power of AI and ML and develop that predictive intelligence. So where are we with Hart Sewer? Very pleased to say that we have a number of live trials ongoing. We've just completed a 3-month trial to Severn Trent Water, which was 10 sites for 3 months and successfully completed. We have a live trial ongoing with Sydney Water in Australia, which commenced earlier in the month. If you can move to the next slide, that would be great, thank you. And the next steps for Hart Sewer are, it was introduced to the market yesterday. The Metasphere team are available for discussions, and product will be available early next year. But we are very hopeful that this is a big step forward for those utilities looking to develop smart wastewater network systems and gain visibility across the whole network at an affordable cost, and to be able to gain the power of AI and ML for predictive intelligence and prevent sewer blockages and spills from occurring. Thank you very much. More than happy to take any questions.
Thanks so much, Paul. I think we've got time for a couple questions before we wrap up. One for you, Paul Hart. Do any of your customers have their systems directly messaging enviro regulators when a system overflows, as opposed to it being managed by the customer itself?
That's a good question. I don't know whether any of our major utility clients have that direct messaging to the Environmental Protection Agency in Australia, for example. I know they have very, very close contact with them and are being increasingly proactive with their sewer monitoring in order to show environmental protection agencies that they are doing everything they can to prevent such occurrences.
Okay, great. One for you, Dr. Paul Chuo. As analytics are time dependent, the more data over time, the better the results. How long did it take for the analytics implementation by your system to reach a stage where there is valuable results that were obtained?
Yes, so I replied online, but for everyone's benefit, it's a good question indeed. You always need time to calibrate your algorithm based on past data and to confront them with live data and live events as well. So on the sewer side, the benefits were almost done instantly because we run the module without direct automation for a few months, provided only as insights. So the algorithm at this point of time had time to basically get calibrated. On the wastewater treatment side, for these features, but also most features, not only stormwater, you usually need the time for setup, training, fine-tuning, and optimization of the set point from 1 to 6 months at most.
Okay, great. And then Thomas, one more for you. How do you determine the first flush? So your worst quality runoff is captured and treated at the wastewater treatment plant.
Yeah, so we don't have a setup per se in this platform to assess if the first flush has been so-called entirely treated at the wastewater treatment plant. What I can say, however, is because we are allowing the wastewater treatment plant to get ready per se into stormwater mode before the wet weather event occurs, we are going to slightly increase the biological capacity, and we are going to equalize flow in the sewer system up front before it occurs. So the first flush is going to be better handled.
Thanks, Thomas. Alana, did you want to wrap it up?
Yeah, we are getting towards the end of the hour, so I will wrap up today's session. I do want to thank everyone for attending today. Any questions that have come through during this session, we will actually follow those up once the presentation's over, so your questions won't be unanswered. We will also be sure to send over the recording and presentations to everyone as well. So have a wonderful day today. Thank you again to all of our presenters, everyone for joining, and we look forward to seeing you at our next SWAN virtual event. Thanks, everyone.
Thanks so much.
All right.